All right, welcome everybody. This is our third and final part for Chapter 3. We are talking about categorical data and how we display and describe it. In this video, we're going to be talking about an idea called independence. Now, one thing that I want to bring up about independence here very first is we bring up this topic several times throughout this course, and we look at it from this is going to be kind of a general introduction to what independence is. Later on, we're going to take a more formal definition for independence and how we look at it in terms of probability. So right now we're doing a very general introduction to what this is. And so what independence mean, variables are independent of each other if one does not affect the other. Okay, so if I'm looking at two different variables, let's think about the Titanic data. Does your survival is your survival related to class, right? Were you going to survive? Was your likelihood of surviving the same whether you were first class, second class, third class, or crew, or was it different? And I think we can remember from those previous ones that no, it was in fact not. You had a significant higher chance of surviving if you were in first class. So that's what independence means. In that case, those were not independent because one depended on the other. Your survival was related to class. In a contingency table, if the distribution of one variable is the same for all categories of another, the variables are independent. So when we're looking at a conditional distribution, if the conditional distribution of one category is the same as the conditional distribution for the other category, then they are independent. Again, let's go back and look at that data. You can see here that the conditional distribution for class, right? We're looking at column percentages here. This distribution, 62.5 to 37.5, is not the same for all of them. So these are not independent. The other way we might say that is that there is an association. It matters what class you're in, because the higher the class, the higher the likelihood that you survived. Unless you were in third or crew, these are close enough together that you might call them independent, just these two, because these distributions are the same or close enough to the same that it doesn't make a huge difference. Okay, so that's what independence means. Does one affect the other? And the way we see that is by looking at the conditional distributions for all the categories of another. Okay, so we can look at the relative frequency of everything in one variable would be the same as the whole. Or we can look to see if one variable is the same for each category of the other variable. This one right here is what we said on the last slide. You can also check independence by seeing if the relative frequency of everything in one variable would be the same as the whole. And what I mean by that is if you have, if you were to look at this as the row percentages, we can check to see if this percent matches the total percent. Not as a 100% though, as if this were, actually, I'm sorry, we should look at that in terms of column. Is this percent the same as the total percent over here? Sorry, I had the wrong slide there. Right, so we can look at this and compare it to the total to see if those things are independent, okay? So let's do an example of this, right? We've got a set of data here of sex and eye color for students in the class. So here's my table. Let's answer a few questions. So this isn't all about independence, by the way. So what percent of females are brown-eyed? I want to draw your attention to the way that this question is being asked. It says what percent of females. So notice that it's giving us a conditional statement, right? That is a conditional statement. It says what percent of females. So I'm looking at only females right now, and I'm saying what percent of them are brown-eyed. Well, 16 out of 32 of them are brown-eyed. which means we're at 0.5. Okay, so what percent of females are brown-eyed? That would be 50%. Notice I wrote as a fraction, a decimal, and a percent. It does not matter how you write that. If you want to write that out, all of them like that, that is a perfectly acceptable thing to do. But I would just choose one, and I would typically just choose either the decimal or the percent. Either of those is better. Okay. Number 2, what percent of brown-eyed students are female? Notice again the conditional statement. What percent of brown-eyed students are female? Okay. I have a specific conditional statement being told. Brown-eyed students are female. So I have 16 out of 36 this time, which as a fraction is 0.44. Excuse me, as a decimal is 0.44, or 44.4%. Okay. So again, conditional statement. What percent of brown-eyed students? That's a conditional statement about brown-eyed students. What percent of students are brown-eyed females? Again, notice the way that this is being asked. It's not giving a conditional statement this time. It's saying what percent of students. So what percent of the whole this time are brown-eyed females? Notice that in this statement over here, we contain part of each variable. A brown-eyed female is 16. We have 16 brown-eyed females. And then it says what percent of students? Well, there's 64 students. So that's 16 out of 64, which is going to be 1/4, or 0.25. So 0.25 is a decimal, or 25%. Again, you don't have to report all 3 of these numbers. Pick the one that you like the most, probably decimal and percent. Fractions, we don't use a lot of in AP Stats. We tend to use decimals. Okay. Moving on. What's the distribution of eye color? So now it's asking for a distribution this time. A distribution would be everything we need to know about eye color. So we would be writing a sentence in this case, where we're going to write all of everything we know about eye color. So this would be, we have 6 blue-eyed males and 4 females. We have 20 brown-eyed males and 16 females, etc., 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 right? We're going to write out everything that we can about the green and hazel also. So it's asking us for distribution of eye color. We're writing out the entire distribution of what we know about eye color. For this one, it says, what's the conditional distribution of eye color for the males? So now we only need to talk about the males. We have 6 blue-eyed males. We have 20 brown-eyed males. Etc. Okay, we're going to write the whole distribution for the males. Again, distribution is a key that I'm looking at the entire table. Okay. 6. Compare the percent who are female among the blue-eyed students to the percent who are female, of the students who are female. So blue-eyed students who are female, we have 4. Excuse me, I think I wrote, yeah. The percent who are female among the blue-eyed students. So conditional statement, we're blue-eyed students. How many of them are female? 4 out of 10. Okay. And then to the total percent of all students who are female, that's 32 out of 64. So here's my blue-eyed students who are female. Blue-eyed females. And then we have 32 out of 64 who are females. All right. So I'm just comparing those percents. We want to make them percents, right? 40% and 50%. And then the final question here is, does it seem that eye color and sex are independent? Okay, so we need to look at these distributions and decide, are they similar when we're looking at the percentages? So we can do two things. Remember, we can look at the distribution as a whole and see if it compares the same as the others, or we can compare a particular conditional statement to the total. Let's kind of just do both here to just to make it a little bit nicer. So let's compare the blue-eyeds with the column percentages. So looking at column percentages, we have 60% blue-eyed students who are male, 40% who are female. Here we have 20 out of 36, which is 55%. And then this one would be 45%. And then this one would be, what is that? 6 out of 18 is going to be 33%. And this one's going to be 66%. Give or take, right? It's 0.6666, whatever. So looking at the distribution, are all of these, does the conditional distribution for males match the conditional distribution for females? And the answer is no, it doesn't, right? Because the conditional distribution for males does not match the conditional distribution for females. It does not appear to be independent. Now, notice the way that I phrased that. I said, it does not appear to be. Notice that I didn't say, it's not independent, because we're not entirely certain if it's not. We're making a guess isn't the right word. We're making an educated guess based on the information that we have here, but this is a relatively small sample size. So we're being a little bit wishy-washy with the answer here, which is pretty good practice when it comes to many things in statistics when we're reporting answers. Saying it does not appear, we're being a little bit waffly there to make sure that we're leaving room for error, because we might be wrong. We can also look at this again by comparing to the total percentage. We can compare the blue-eyeds to the totals, or the browns to the totals, or the greens to the totals. And again, in all of these cases, it does not appear as though the percentages match. All of these are different enough that we don't believe that they would be independent. The brown-eyeds get kind of close, but clearly the green and the blue are pretty far away. So it does not appear to be independent based on the data that we have. And that's it. Oh, no, wait, that's not it. We're going to talk about segmented bar charts. But that's it with independence. Again, remember, it's all about is there a relationship between the two variables, okay? And we look at that relationship looking at the relative frequency, the contingency table. Finally, the last thing, here it is, a segmented bar chart. And this is just a really quick thing here. Segmented bar charts are like pie charts or bar charts. It's just that on the bar chart, instead of there being multiple bars, we have a single bar. And notice that in each of these cases, we have a proportional color, right? The proportional amount of dead, and the proportional in the crew, and the proportional amount in the third class, second, and first. So of the dead people, you can see clearly many more of them were crew than third class, than second or first. Okay, this whole thing represents 100%, so it looks like about 45% of the crew died, and then let's see here, 80 to 45, that's about 35% here, and then we've got about 10% here, and then about another 10% here. I think this is like 12%, it's slightly higher. Okay, So segmented bar chart is basically, it's the pie chart of bar charts, if that makes sense. And that, I think, is it. That's definitely it, okay? So here we have everything from Chapter 3. If you've got questions, comments, or concerns, make sure to leave them in the comments, and I'll get to you. Thank you very much for watching, and have a fantastic day.